Hey everyone, hope you enjoyed that quick little video. I'm Shaya, the same guy in the video, and I was invited here to talk to you on behalf of Polyup. Sorry I couldn't make it here today in person, so I'm pre-recording my talk instead. I'll be available to answer your questions at the end, live. So there's this piece of advice I've heard in a talk I listened to recently, that people learn best through stories. Everyone's situation is different, so it doesn't make sense to just tell everyone your ideas. Your story and how you got there is equally important in getting your message across. So I'd like to split this talk into essentially two sections. First, I'd like to tell you the story of Polyup, to put our work into perspective. Then I'll show you the learning environment we have created, and go over more the material in my paper. So the idea for Polyup kind of began a while before the company. I'm sure many of you have heard of Professor Yahya Tabesh. He's an esteemed math and computer science educator from here in Iran, and he's actually won the Erdosh Award, this international medal awarded every 2 years for work done in math education. Even more relevant, he actually co-founded Iran's IOI team. Yahya has spent his life dedicated to helping young people acquire a joy for computational thought by setting up a variety of math houses and math competitions in Iran and more. I highly recommend you look into his work. Well, a few years ago, Yahya came here to the US. At the time, he was writing a book on problem solving, along with a couple of his former students from Shaya University, and he asked me to help refine and add to his ideas. I was honored to join him. So we set off, writing and editing this book of his, when we began to realize how hard it was to teach people something so inherently interactive in such an inherently uninteractive way. Like, if you want to read a sequential story, a book is great. But if you want to show people a visual problem and ask them to solve it, honestly, books suck. So, we decided that video games were a much better medium for interaction, to allow learners to truly learn by doing, not by passively reading something being taught at them. And so, Polyup was born, with the aim to empower a global community of problem solvers, using the medium of video games. Yahya and I teamed up with my dad and another serial entrepreneur to build our co-founding team for Polyup, and we set off to educate the world. So at this point you might be thinking, oh, Polyup is just another fish in the sea of educational games. And in a sense, that's true. There were and are a lot of educational apps on the market, especially in the math and coding marketplace. But the thing is, most of these apps are geared towards a certain curriculum, teaching kids some specific skill for the math apps, or a specific syntactical paradigm like Java for the coding apps. Very few of these apps tapped into the core pillars of problem solving, which at Polyup we call computational thinking. There's a definition from Carnegie Mellon right there. It involves the ability to decompose problems, find patterns, abstract these patterns, and build computational algorithms, which are key to becoming a truly creative problem solver. One who can tackle entirely new problems based on previous knowledge, rather than reapply simple procedures or formulas to solve the same kinds of problems. But really, the apps we saw focused on procedures, like solving single variable equations or writing a for loop. None of them truly tackled this core of problem solving. So computational thinking became our mantra at Polyup. Everything we did, the games we made, were to instill computational thinking skills. Our first prototype, which we called Square Hunt, was all about finding squares on a grid. It was a decent game, but we realized how limited the scope of having just one problem was. Also, it was pretty childish, and we wanted to create something that would appeal to all ages. So about a year ago, we created an entire suite of puzzle games, modeled after the types of problems found in Yahya's problem-solving book. We went around showing these games to a bunch of teens, and the response was pretty positive. Here are actually a couple of screenshots from these games. We had some really high-quality content here. The puzzles were fully interactive, and in my opinion, were really effective in instilling computational thinking skills. Only there were two problems. First, on the development side, the very essence of these unique puzzles meant that creating each puzzle took a really long time, especially when you compare it to how long a user could enjoy it. And second, it's really hard to attract users to play web games, especially when you tell them they're about math. Over the past couple of years, we've gone through iteration after iteration of prototype, and we have tested them in various schools. We decided we needed to make a mobile game to make the app more visible on the open market. And we also decided that we needed a unified theme for our puzzles to make large-scale development manageable. We went through a whole phase of putting a mathy puzzle in the middle of a more classic phone game, like the one here. But we realized we couldn't just trick people. If the math part of the app was boring, we couldn't just cover it up with a regular game and expect users to play it. Either we'd lose educational value, or people would just play a game where they didn't have to learn. Basically, we learned a valuable lesson. You can't trick people into learning. You have to make the learning fun. And finally, after about 6 months ago, we got it. We figured out a learning environment that, 1, could fit in a mobile app for widespread use, 2, had a unified system for puzzles, and 3, it didn't hide the educational aspect. It made it fun. So now's the part of my talk where I get into exactly how this environment works. And honestly, if I say so myself, it's put together very well. We've created a casual programming environment that is at the same time one-handed and Turing complete. Turing complete just means that any computational task that can be carried out by a computer, the same algorithm can be carried out by our programming environment. One-handed means, well, you can code using your phone with just one hand, like while you walk or something. Like a lot of other educational programming environments, Polyup's app is block-based, but that's where the similarities end. Now, before I go into what makes us different, I wanted to touch again on the plight of educational apps in a little bit more depth. If we take a look at existing coding apps out there, a couple of commonalities appear that we think detract from the educational value.
So we had some technical difficulties here, so I'm going to be speaking like this for the next few minutes. Just hold on and carrying on. So I know I touched on this before, but I want to visit, say, the plight of ed apps in a little more depth. If we take a look at existing coding educational apps out there, a couple commonalities appear that we think detract from the educational value. First, many apps are too focused on the syntax of some specific language, like Java or Python or C++. The focus on, say, Java's quirks, things like the meaning of that pesky public static main message, or figuring out the exact syntax of a for loop with all the semicolons and parentheses perfectly, takes away from the focus on computational thinking, which is kind of our mission in Polyup. But, this problem doesn't apply to all of these apps. You have some block-based languages that kind of package the main components of a program into blocks. But even these apps have the second problem. They're all procedural. Everything is just a set of steps running sequentially, or maybe at the very advanced stages over and over in a loop. But the thing is, important algorithms used in the real world are rarely just sequential. More often they include things like recursion, like multiprocessing, all of which are taught very poorly in most environments. Either recursion is introduced as some super hard concept after everything else has been covered, or it's not covered at all. And it's inherently hard to teach recursion in a procedural coding environment, because the order of events is just so unclear. And it's not just recursion too. Whenever you have multiple methods interacting with each other dynamically, it becomes really hard to keep track of in a procedural environment. So even that goes untaught. So our programming environment fixes these two problems, to forget about the minutiae of programming, the little things, and focus on just one major idea, the logical way a computer works. So first, instead of being procedural, Polyup uses a functional programming paradigm. The difference is a little hard to explain. Functional programming is a programming paradigm, basically a style of building the structure and elements of computer programs, that treats computation as the evaluation of mathematical functions and avoids things that kind of take away from that, like changing state and mutable data. Programming is done with expressions or declarations instead of statements. In functional code, the output value of a function depends only on the arguments that are passed into the function. So calling a function twice with the same value for an argument x will produce the same result f of x every time. But think, in a procedural language, variables have a local or a global state, so the program can have different states even when you're running the same code. So functional programming is extremely important because it removes the focus on the state of the program's variables, and instead it presents the program as a single logical series of transformations. It's kind of hard to speak of this in solely theory, though. Let's take a look at a few examples, and the impact of functional programming will probably become a little more clear. Second, we're using a block-based language with reverse Polish notation. Block-based, I already said, it kind of takes away the focus on the minutia. Every single character has to be perfect. But reverse Polish is especially important because it means that the function comes after the operators in the compiler. So, for example, instead of doing 7 plus 2, you do 7 2 plus. It may be hard to get the hang of it at first, but it actually helps the user think of numbers and operators in a whole new way, with operators as functions. It also makes Polyup's environment look and feel a little less like school math. It's something new, right? It's like the plus function is being applied to the 7 and 2, not just 7 plus 2. But even more important, the reverse Polish notation makes parentheses obsolete. Say if you want to do 7 minus parentheses 2 minus 2, you can just put 7 2 2 minus minus. Again, we're removing the minutia of programming.
Third, we deviate from the typical learning path by what we call learning by teaching. It's well documented in pedagogical literature that teaching others can be one of the most motivating ways to master material yourself. So Polyup has an AI sidekick, which we call Poly. You saw him earlier in the short little video too. As you solve puzzles, you show Poly how to solve them too. We combine learning by teaching with dynamic scaffolding, which is essentially having every user go through a personalized progression of levels, dynamically based on their performance. Things like how fast they solve the puzzles, or how many incorrect tries they get. So let's take a look at what happens when we put all this theory together. Here's a quick little demo of one very simple program written in PolyScript. This is the same one from the video. Poly is at the bottom of the program, and you have the 2 circle blocks followed by the square operator. The plus operator eats the 2 inputs and produces an output, 9. And this very visual method is extremely effective and gamifies the very essence of a function. It physically takes in some inputs and as a result creates some output. And when you stack a bunch of numbers and operators together, you get something that looks like this. This is where the functional style of the language comes into play. There's really no specific statements, but rather every single function is a stack of numbers and operators. So if you just put more numbers and operators together, like in this one, you get more computation. Now, these are just some of the basic puzzles. If we want to show the full potential of the programming language, we can make our own workspace. And the editor here actually has up to 6 panes. You have the number pane where you can make any number a decimal, the math pane where you have the 4 basic operations as well as more complicated ones. The math pane is actually super cool because the user can actually add his or her own functional programs as functions to the math pane. You also have the variable pane, which has where you set and use variables, the Boolean pane that has true, false, and inequalities, and a couple more panes for referencing other functions. Now, we saw it in the 7-2 plus puzzle, but the magic in Polyup lies in its extremely simple compiler. The program starts running at the top of the stack and just keeps going down until it sees a function block. Then the function block takes in the appropriate number of inputs and creates the output. And it just keeps going. If there's a reference to another function, it'll just add it to the stack. So things get really interesting when you put multiple functions together, like right here. The script here is actually the factorial function. So let's take a step back. There are 2 ways to calculate x factorial. One is the usual procedural definition. Here, 4 factorial would be calculated as 4 times 3 times 2 times 1. Now, in the functional definition, we use recursion. Here, x is defined in terms of x minus 1 factorial, as x factorial equals x times x minus 1 factorial. So by expressing the function as a function of the number before it, we expect the computer to figure out how to calculate 4 factorial as 4 times 3 factorial. But then 3 factorial is 3 times 2 factorial. 2 factorial is 2 times 1 factorial. Now, we need to do something about 1 factorial, or we'll keep going to get like negative numbers. So we need to add the base case 1 factorial equals 1 to the functional description. So how does the PolyScript work here? Now, the first stack asks only for the input value x to calculate x factorial. Now, the diamond here is just a reference to another stack. Here it refers to the second one. Now, the second stack shows the main factorial function definition. The first block sets x to the value above it by eating 1 block above it. And this block at first comes from polystack. Now, see this third stack? It's just a different way of writing x factorial equals x times x minus 1 factorial. Right? There's an x, then there's an x minus 1, and before multiplying the 2 together, we have to get the factorial of the x minus 1. And to do that, we just send it back to the top of the same stack that defines the factorial function, that's stack 2. Now the only thing left is checking if the number has reached 1. That's what the if statement does. If x greater than 1 is true, it continues the recursive calculation. If it's false, then it just returns 1. So now we have our base case, and the program is complete. So now let's try running this program. You see, it recursively creates the 4, and then the 3, and then the 2. And the best part is, along the way, the multiplication signs stay at the bottom, just waiting for the recursion to finish. In a procedural language, this would be all but impossible to show. But in our functional style of programming, it's natural. You see, Polyup's visual environment is very powerful to show not only recursion, but also debugging in case something goes wrong. There are no core dumps, there's no crashing. Say, if we didn't put a base case, the program would just keep running into the negatives. Whereas if you did the same thing in, say, Java, it would just never finish running. Because with PolyScript, it shows you the program as it runs. It shows you every single computation the computer does. Now, what's even cooler, we've shown this factorial program to kids in 6th grade, and they've grasped the factorial function in 35 minutes from their first introduction to Polyup, while they had no prior computer science class. A lot of them have never even heard of the factorial function before. Now, finally, I'd like to show you a more advanced function. The McCarthy-91 function is a recursive function defined by computer scientist John McCarthy as a test case for formal verification within computer science. The McCarthy-91 function is defined as m of n equals n minus 10 if n is greater than 100, and m of n is m of n plus 11 if n is less than or equal to 100. The results, if you evaluate it, are m of n is 91 for all integer arguments n is less than or equal to 100, and m of n is n minus 10 for all arguments greater than 100. So m of 101 is 91, m of 102 is 92, and so on. So most people that learn standard programming will have a hard time seeing why this function has this behavior. So let's look at it in PolyScript. As you see, it's super natural to have a nested recursion defined here. If you see the run, you'll get a great view on why the function has such surprising results, always ending up to be 91 for any number less than or equal to 100. See, the program took 562 steps to run in a wildly nested recursion, but everything is readily available to the user. To summarize, we have developed an innovative new platform for learning computational thinking. The best part, there's no age limit on the platform. It can work for anyone from 7 to 70 years old. From learning the order of operations for basic arithmetic to providing puzzles at the Olympiad level, it works for anyone. I mentioned this before, but we're using dynamic scaffolding to personalize the difficulty level to every user. So we've gone and shown this environment to schools, and they love it. They rate it, depending on the school, anywhere between 7.5 and 8 out of 10 for how much they like it. So where are we taking this? Well, first, we're working really hard on making Polyup social. Now, there's two ways we're doing this. First, we're having a Google Docs style view where two people can work on the same workspace. Second, we'll let players send each other puzzles to solve with PolyScript, kind of in a challenging mode. Now, finally, I want to touch back on what I was talking about in the video. We want Polyup to become a hub for casual modding. The casual programming environment we've created really lends itself well to changing rules and numbers in existing simulations and designs, to mod or modify them, and make them your own. We currently have a few basic mods and are working on more substantial ones. In the future, we'll build integration with hardware and software, say NXT robots or Minecraft, to make Polyup a truly universal place to mod your devices and tools. Now, why modding? Well, at Polyup, we think modding is really important because the amount of effort needed to change a working piece of code is far less than the amount of effort required to create it. This really improves the amount the user gets out of his time and makes the experience much more rewarding. So we think modding will be an extremely effective way to bring computational thinking to the masses. Instead of forcing users to use a new product, we give them the option to toy with the things they know and love using our app. So, on that note, I'd like to open things up for a bit of Q&A. It's around 12 a.m. where I am, but I've stayed up for all of you.
Okay.
Yeah. Forcing users to use a new product. We give them the option to toy with the things they know and love using our app. So on that note, I'd like to open things up for a bit of Q&A. It's around 12 a.m. where I am, but I've stayed up for all of you. Thanks, and I'll see you live.